on recent advances in geotechnics for infrastructure. We call it as ROGI 2020, a virtual webinar. Sir, can you hear me?
Yeah, loud and clear. One second, I'm having a problem again. 1 second, sir. If there is any mobile close by, I would appreciate if you can keep it somewhere else, sir. Definitely not close to the CPU.
Kept it aside.
Okay. Yeah. Can you talk for a while, please, so that I do the audio check? For 1 minute.
So good morning. For the past 2 days, we have a very fantastic presentations, which gives an insight into the value addition of the role of geotechnics or geotechnical testing procedure at the construction sites, so that we can encompass a lot of problems related to foundation engineering or ground improvement techniques, or the techniques by means of which we are going to do the geotechnical exploration, etc. So is it clear, sir?
It's very clear, sir. Yeah, you are loud and clear. Another 2 minutes, we'll start the event, sir.
Okay, sir. Okay.
Anil sir, should we start in another minute's time, sir? 57.
A very good morning to all the construction professionals who have logged in, and to the speaker of the day, Engineer ANIRUDHAN, who has taken time off from his busy schedule to speak to us. And we also have Dr. H.S. Prasanna over here. A very warm welcome to the speakers, both of you, and to all the construction professionals. Now, let me just take a few moments to introduce the speaker of the day, Dr. Engineer I.V. ANIRUDHAN. He is the CEO of a consultancy firm, Geotechnical Solutions, at Chennai, and has carried out several geotechnical investigations, studies all over India, and a substantial experience in the construction of bored cast in situ piles and driven cast in situ piles. He has designed and executed several ground improvement programs involving rammed and vibrostone columns, sand drains, PVD, etc. He has carried out several consultancy works for sewage treatments, plant, water treatment plant, effluent treatment plant, desalination plant, power plant, fertilizer plant. He is presently a consultant to some of the leading consultancies, consultancy firms and turnkey contractors. Engineer I.V. ANIRUDHAN completed graduation in civil engineering at from Thrissur Calicut University in 1979 and obtained masters in geotechnical from IIT Kanpur in 1981. He has published and presented technical papers in many conferences and seminars, and has written a manual on lateritic soil and edited the general guidance for geotechnical investigation by TC04 of Indian Geotechnical Society. So that's the speaker of the day, Engineer I.V. ANIRUDHAN. We also have Dr. H.S. Prasanna. Let me also take brief moments to introduce him. He joined National Institute of Engineering in the year 1987 and is presently working as a professor in civil engineering department. He has had several experiences, having worked as estate officer and as well as managing the placement cell of NIE. He is actively involved in the geotechnical engineering as a researcher, guide, and active geotechnical consultant. He has worked for almost 1,500 projects. He is currently guiding 5 PhD students for the doctoral program and 1 MSc student. He has conducted many national workshops, seminars, webinars, and he is also a member of Indian Geotechnical Society and Association of Consultants Civil Engineers, Mysore. He has published around 30 articles in peer-reviewed journals, conference proceedings. He has had talks at CRS, Institute of Development Studies, Administrative Training Institute, Karnataka Engineering Research Station, and various engineering colleges. So that's Dr. H.S. Prasanna. Welcome you, sir. Welcome Engineer ANIRUDHAN also. Now, before we go on to the talk, let me also thank the organizers, the Association of Consulting Civil Engineers, Mysore Center, Indian Geotechnical Society, for having organized speakers of repute and who are experts in the area of geotechnical engineering. So I am sure that the first 2 talks that we had by Professor Madhav and Engineer Mohan Prasad yesterday on various aspects of geotechnical would be an eye-opener, because the first talk was on innovative solutions in geotechnical engineering, and the second was on misconceptions in the area of geotechnical investigation from a very practical perspective. So today's talk is the 3rd talk of the seminar, that is of the conference that we are having. And tomorrow we have the final and the 4th talk of the conference by Professor Dodagowder of IIT Madras, and he would also be talking about materials as well as various aspects of geotechnical engineering. And I am sure that these 4 talks would be one of the top class talks in the area of geotechnical engineering. And we at Ramco Cements are indeed privileged to have the speakers and as well as to collaborate with the associations for this knowledge dissemination, because what we believe as an organization is that our customers and the construction professionals should be aware of the recent developments and the practices that is happening across the country as well as the globe, because that gives everybody an idea to implement new ideas as well as to think about innovative solutions, whether it be the area of concrete, whether it be the area of geotechnical engineering, whether it be the area of reinforcement detailing. We had a webinar on reinforcement detailing as well, and smart cities, ready mix concrete. We had number of webinars starting during the lockdown, and this is the 26th webinar that we are having as far as the Ramco Cement is concerned. So with those few words, and another very important aspect is that this interaction with the construction professionals has helped us to understand the various challenges in concreting. Thereby, we have been able to customize our cement products based on the various concrete requirements. So now presently we have 12 cement products. OPC, ordinary Portland cement itself, we have OPC 53 infra, which is being used for concrete with longer slump retention. That is, if you want a slump retention of about 3 hours, if you want to transport the concrete for about 3 hours, OPC 53 infra is there. For precast works, we have Ramco Super Fast, which is again being used in many precast units across the country, and many of them have got the advantages when they are using in the precast unit in terms of early gain of strength and things like that. So this has been a wonderful experience for us, and we have been able to customize the cement product, and as well as we have the dry mix range of products, for non-structural applications. So I mean, this kind of interaction would help us to collaborate, and at the end of it, what we need to do is that we need to be a solution provider, and that is what we are attempting to do. And we have a research center at Chennai, the Ramco Research Development Center, which is doing a lot of studies on cement, concrete, and we have a database of concrete mix designs with various chemical admixtures, because one of the most challenging aspect is the cement admixture, and we have been able to give those solutions. So with those few words, I welcome the speaker of the day, Engineer ANIRUDHAN sir, to take over and to enlighten us about today's topic. Over to you, sir.
Yeah, thank you, Anil, for your kind words of introduction. Am I audible to you?
Very much audible, very clear.
Yeah. So, namaste to all of you, all the listeners of this webinar. So, I should congratulate all the associate members of this virtual conference. And shall I start the presentation now? I hope you are able to see the screen.
Yes. You can make the slideshow.
Yeah, it's slideshow only, but I did not use the full screen width because I don't know. Because many may be using the phone, so I made only a square type presentation. So let me say a word of appreciation to ACCI.
Now we are not able to see the thing, sir, the screen, the presentation.
Yeah. So ACCI, then Ramco Siemens, IGS Mangalore chapter, Mysuru, and SJCE Mysore for conducting this workshop.
Anirudhan sir, sorry to interrupt. The file is not visible. Can we do it again, sir? It's not visible to the participants. Share screen. Can we do it again, sir, please?
I will do it.
I will move you away from being the presenter, and I'll. One second, sir. Okay. It's showing as low bandwidth in Anirudhan sir's place, but worst case scenario, we will check again, sir. And if necessary, we can mute your video as well to ensure that the PC is on. It's taking a while. No, sir, it's not visible again. Can we share it using file on the screen? Your mic is muted, I suppose. I'll unmute it, sir.
I'm sharing by screen only, by file only. Let me let's share by screen. Able to see now?
It's taking a while to upload. Let us check, sir.
It will take some time, sir. It is starting to share content. It's coming, I think, because of the bandwidth.
Oh, wonderful. It's visible now, sir. Wonderful.
Now it's visible.
Shall I proceed now? You are able to see?
Now we are able to.
Yes, sir. Please proceed.
Yeah. So I was appreciating the effort of all these members of the program committee for conducting this virtual workshop on recent advances in geotechnics in infrastructure RE 2020. I also personally thank my friend Professor S.K. Prasad, whom I met in 2003 in IIT Kanpur, for inviting me to this program. And when I promised him to talk on some case histories, and then I remembered this cartoon picture. So I sincerely hope that I am not going to bore you with so many case histories, especially when we approach to the lunch time. So my attempt is to talk on the significance of case studies in geotechnical engineering practice. All we know that geotechnical engineering practice have come into existence because of a lot of case histories, a lot of failures, and after studying a lot of failures. So we'll have so many famous case histories all over the world, and some of the most celebrated case histories around the world are: there was a bearing capacity failure of Transcona Grain Tower, Canada in 1913, which was later straightened by the effort of several engineers and engineering minds. In Mexico, there are so many damages for different buildings, mainly because of the groundwater lowering and construction of adjacent buildings, and also by the influence of heavy buildings to buildings on the adjacent light buildings. So the light buildings got damaged because of the interference from the heavy buildings. So these are a lot of cases such like that in Mexico. And all of you know the Pisa Tower, Italy case, which is a well-studied foundation issue. And there are so many, numerous number of papers on Pisa Tower foundation. And one of the celebrated case history is a reticulated wood pile technique that was used for earth retention construction of Postwall Tunnel in 1997. This is close to Manchester, and where they used a series of micropiles interacting with each other to support a 14-meter high earth for the reconstruction of the tunnel. And we have more recent cases like Nicole Highway collapse in 2007. Then we have Burj Khalifa Tower, which has which has no issues, but this is a good case of piled up foundation where the expected settlements were much less than the actual settlements were much less than the expected settlements. We have the case of Millennium Tower in San Francisco, where there was an issue of building and settlement. These are more recent ones, and many research papers are available on these structures. When we come to the case histories from India, we are very much open to all the case histories, which is evident from the conference, this workshop, like this Ragi, as well as there are several sessions during the IGS Indian Geotechnical Conference every year. But there is a lack of well-documented case histories in India, because of which we do not know much researches and advancements happening all over India. So my attempt is to present some of the case studies which I came across and see what contribution it makes to the engineering practice. All these case histories are reasonably well documented by me in some of the conference proceedings. I shall present 4 cases if time permits. One is the behavior of single pile and behavior of large pile group and how does it relate, and load settlement response of a pile and design and its design consequences. And there is a case of tilting of a wet slope tank in one of the refineries. And lastly, the restoration of a cooling water channel in NTPC, Kaniha in Thalcher. If time permits, I will briefly show some pictures of efficacy of laterite blocks in gabion construction. So this will be the structure of my presentation. I will start with the behavior of single pile and large pile group behavior, which will show why a detailed settlement analysis of a large pile group is necessary. So one of the famous pictures in the book by Geotechnical, in which R.D. Chellis wrote a chapter on pile foundation. This picture shows the fallacy of testing an action of single pile. You can see that under the test of a single pile, the clay is unloaded. The weak clay below the pile is not loaded. Whereas when under the completed structure, it is heavily stressed, resulting in large settlements. So this is one of the fallacy between single pile testing and when it actually behaves in a group. So I will take you to one of the largest fertilizer plant in Paradip, where we had several large storage tanks holding ammonia and acids, and some of the fuel oil tanks. Most of these tanks were supported on short piles, large number of groups. These ammonia tanks were 33-meter diameter and phosphoric tanks 28-meter. And we had sulfuric acid tanks of 28-meter diameter and some fuel oil storage tanks with smaller diameter. These were constructed in early 80s, and all these tanks are performing well now. If you look at the foundation of one of the lower storage tank, the 33-meter ammonia tank, we had 437 numbers of 450 mm diameter 21 piles, passing through loose fill, soft clay, then resting in medium dense sand. Below the pile tip level, we had dense sand and medium stiff clay layers. These clay layers were compressible in nature, and we expected large settlements. So a detailed settlement estimation of the group was made using the standard procedure of people and raft. And post-next stress distribution you can see on the left side. You can see the influence zone of the large group under the ammonia tank structure. On the right side, you can see a single pile. When we take one pile out, and how does it influence, or how is it influenced by the soil around? It's a small soil just around the tip is influencing the performance of a single pile if it is not under the group. So this is the detailed settlement analysis summary for the 3 ammonia tanks. The first one was with a smaller length of pile, roughly 10 meters, and we got settlement of the order of 160, 142, 170 at the center, and 89 to 100 and the periphery. So we modified the estimations using the Mayer corrections, and again applied with the correction for interaction between the piles. So we expected a settlement of the order of 100 mm towards center and roughly 70-75 mm towards the periphery. And there is also an estimation when the tank is not supporting on the pile, only on natural soil. The large, we expected a very large settlement of 300 to 350 millimeters in the center. We, of the 437 piles in one group, below one ammonia tank, we tested 5 piles, and this is the performance of one single piles towards settlement response. We got roughly 4 to 5 millimeter settlement when the pile was loaded to 1.5 times the design capacity. The design capacity was 55 to 65 tons, and these piles were test loaded up to 1250 kilonewton. After the tank was constructed, and there was a necessity for hydrotesting, and the tank was hydro-tested for a period of about 9 months in total. So each load increment of 1 meter to 2 meters were kept for a long period of time until the settlements were stabilized. So we can see the settlement. The firm lines are the settlement at the center of the tank, which is of the order of 65 to 103 millimeters, and along the periphery it was 50 to 78 millimeters. So these settlements were very close to the estimated ones, and we can see the bowl shape of the tank foundation. The dotted lines were the actual settlements, where the firm lines are the estimated ones. So we have a close match with estimated and actual performance of the tank. And we got a bowl shape final profile of the raft, connecting raft. All these piles were connected with this common raft, which is not very thick, and it was flexurally designed to support this sort of differential settlements. This is another presentation of the settlement. Along the periphery, you can see almost uniform settlement under each load increment, went up to around 63, 64 mm for tank 2 foundation. And we can have a comparison with the performance of a foundation on natural ground, marginally treated with a compacted soil in the top. And for this is for a fuel oil tank with a ring wall foundation. These tanks settle, this foundation on this tank settled by about 160 millimeters in the center, and we had settlement of 121 to 140 on the periphery. Whereas in the under the same loading condition, these piled foundations, which is much larger in diameter, settled less than 42 millimeters. So this is for the comparison. I have taken the load of 10 meter of water load in both the cases, and there is a large difference between the settlement offered for these structures. So what we take from these case studies, we have load settlement response on single pile, which is influenced by the share of the skin friction and bearing, and the soil conditions only around the base. Whereas in the case of large groups, the influence goes much deeper, and we need a detailed estimation to see whether the foundation is safe. And there are standard procedures available for estimating the settlement. And it also shows the piles under raft reduces the foundation settlement to great extent. And also the settlement is relatively uniform if the soil conditions are favorable, unless there is a very large difference in the soil conditions below the one foundation. So this was my first case study. Then I'll go to a little further on the load settlement response of a single pile and its design consequences. Mostly we have foundations with 2 or 5 or 6 piles in a group, and there will be some settlement issues when it is a group, but it all relates to the single pile response under the load. I'll show how can a load settlement response from routine load test can mislead the actual performance of the pile. So these are some of the load settlement response curves from routine load test. Routine load test, when we refer it, is we load the pile up to 1.5 times the safe capacity. Here the design capacity is 300 tons and the ultimate capacity is 600 tons. So these piles are loaded up to 450 tons, 1.5 times the design capacity. And we have IS 2911 Part 4 recommendations in which the serviceability criteria is defined, such as when we load the pile up to 1.5 times, the settlement should not be more than 2% of the pile diameter. So these piles are 760 millimeters and 2% of the pile diameter is 15.2 millimeter. And the shaded area on the screen, on the graph, is the limit of settlement of these piles when it is loaded to 1.5 times the safe capacity. Now, if we project one of the pile, the load response curve towards the failure, you can see the curve which is projected and another curve from the other load test results, then the third one from one of the other load test results. So we can project roughly so what we find here is when we project the load settlement response to a close to a failure condition, most of these piles except 2 may not have factor safety 2 against failure, that is ultimate capacity. That is, even though it satisfies the settlement criteria of serviceability criteria under 1.5 times safe capacity, it may not be safe with respect to the ultimate state criteria, which is the factor safety should be more than 2 when the pile settles more than 10% of the pile diameter. We look at some results of the test piles, which are all gone to the failure condition. So these are also of 760 millimeter diameter, both persons 2 piles, and you can see most of the piles have gone to the failure condition. So if we look at the criteria in 2911 Part 4, see this 2% pile diameter, the settlement is 15.2 millimeter, and you can read the corresponding loads from these curves. And we will also have the failure criteria of 10% pile diameter. and compare the safe capacities derived from these procedures as stipulated in IS 291 Part 4. So this is a tabulated form in which the safe capacity using the first criteria of 1.5 times the safe load, we get 2,400 one of the piles, and the corresponding safe capacity from 10% pile diameter criteria is 50 kilometer. So in all the cases except TP5, we have reduced factor safety when it goes to the ultimate failure. So there is a issue when we decide the safe capacity based on the first criteria. Unfortunately, during the routine load test, we do not go to the failure condition. We have settlements close to 1.5 to 2% of the pile diameter, and we are not able to tell how these piles are going to behave when ultimate load reaches. So what we see here is routine vertical compression load test on piles may not exceed the limit of limiting settlement 2% of the diameter. But there is no confirmation on factor safety 2 against ultimate capacity because we have no way of knowing. The factor safety can be less than 2 for a friction dominant pile, and a detailed analysis of load settlement response is necessary to confirm the safety factor. So this is very important when we want to really assess the actual performance of the pile during the life of the pile foundations. There are procedures we can from which we can estimate the ultimate capacities from a reasonably well-developed load settlement response curve for single piles. Now I come to my third case, tilting of a wet slope tank. Storage tank holding wet slope oil in one of the refineries. Here, this is a case of how we are disconnect between the design and the field environment. The design was done for certain site conditions, and the actual field conditions were different. So these are the tanks of 10.8 meter diameter and 13.9 meter height for storing wet slope. And it's with a conical fixed roof condition. And these tanks were resting on ring wall foundation at 3 meter depth, overcoming 2.5 meter thick fill of lateritic soils. So the ring wall will confine the soil inside the ring wall, which will try to transfer the load through hoop into the ring wall. Then the load is actually transferred to the depth of the ring wall foundations. So for the sake of supporting the wet slope tank against wind load, there will be anchors connected to the ring beam. So these tanks are resting on the ring beam directly, not in the earth inside. And we estimated a settlement of 50 to 70 millimeters under the full water load of 13.4 meter. That was the estimation, and there was a requirement of performing the hydrotest, especially for allowing all the settlement to happen before calibrating the structure. So we got settlements of the order of 20 millimeters on the northeast point, and opposite side we had 76 millimeters, and it was gradually increasing from the lowest point, some 20, then 30, 45, 61, 76. On the other side, we have 40, 59, and 79. So there was a tilt of the tank. This was when the tank was loaded, only 50% of the total water load, that is 7 meters of water. And there was an alarm bell put by the owners of the tank. So there was the settlement towards southwest was increasing under the load of 7 meters, and there was a danger of failure, possible failure, and the tank was asked to stop the loading with further water load, and the tank was immediately unloaded.
Now one thing, sir, Maybe 1000 mela.
The site condition during hydrotest.
Okay.
So, shall I continue?
Sir, there's some disturbance, I believe, from somewhere.
Sir.
Let me just find out. How long?
I don't know.
Find out, sir.
So I will continue. I think I will not lose time. So this was the ideal, the condition at which the design was made. It was actually in a cut, and there was supposed to be a reinforced earth filling with the gabion wall bracing. And there is an 18-meter space from the slope, the constructed slope, and between the slope and the actual tank. In reality, the actual site condition was different. The site development was not completed when the tank was hydro-tested. You can see a very steep slope of 1 in 6, very close to the tank, wet slope tank. That is about only 2 meters, less than 2 meters away from the steep slope. So there was, it was suspected that there is a foundation failure, or the soil was trying to move towards the excavation site, and the tank tilted towards that. We would have had the failure, what is shown in the bottom of the picture, if the loading was continued. Fortunately, this failure was prevented by unloading the tank. And we had to take care of how do we go about further hydro testing. So the site development was taken up, and the reinforced earth wall was constructed to form the dike wall area. This reinforced earth construction was used in that. We also put some steel pipe piles around the tank foundation, where we suspected some movement of the foundation. So these piles were supposed to hold any further movement of the soil. And all these piles were connected with the pile cap ring beam, so that possible movement towards the actual initial failure is not happening again when we hydro test it again. We continued with the hydro test of the tank, and we got settlements of the order of 20 to 40 millimeters further from the already happened settlement. If you look at the tabulated form, we had a settlement 25 to 75 millimeter during the initial loading, after which we discontinued and did the site development. Then we had 19 to 43 millimeter settlement when we hydro tested further to the maximum full height. You can see the cumulative settlement after the full height hydro test was 45 millimeter on one side, and other side we have roughly 120 millimeter settlement. There was the settlement of the tank was stabilized over a period of 2 months, and we found that there will not be any further settlement of the tank. But the final tilt remained the same, roughly 74 millimeter over a span of 11.5 meters. So always we have a concern of tilted oil tanks, because the primary concern being the structural stability and the deformation of the shell and base. And there is also a concern on the calibration of the tank and sustainability of the calibration. We may have to do more frequent calibration, volume calibration, to see that the tank is giving actual volume we expect to hold. It is expected to hold. And the tilt is visible. There is a aesthetic concern, which one can decide whether we have to live with that or we have to change it. So regarding the structural stability, we should study further how stable the structure, the base of the tank and the shell of the tank. So it depends on the tilt of the tank, whether it is a planar tilt. When we call planar tilt, the base of the tank is tilting along the tilt. There is no deviation from the tilt line. Whereas if we have the base moving away from the planar tilt line, we call it as non-planar tilt, which can damage the tank structurally. This will induce a lot of, if you have a non-planar tilt, it can induce a lot of stress in the base as well as in the shell. There are several ways of doing estimating the planar tilt, one of the famous being Allen-Mar's procedure. So this orange, the line is the analytical computation of the planar profile, whereas the blue line is the actual profile of the base slab or the shell bottom. So here we will find both the analytical and the planar profile and the actual profile is very close, and generally we can say the tank had a planar tilt without much deviation from the planar tilt profile. We have roughly 4 points of 7 millimeter out of plane settlement, and there is a base tilt of roughly 75 millimeter from northeast to southwest portion of the tank. So as summary, we can see the maximum diametrical settlement was, different settlement was 78 millimeters, which is projected over the height as 102 millimeter. This tilt is acceptable for a tank with conical fixed roof system, and freeboard was 550 millimeters. However, the freeboard was reduced to 430 millimeter because of the tilt, and the owners were agreeing to that reduction. And the maximum out of plane settlement of the tank was 4.7 millimeter, which was not of any consequence as per the provisions in API code 653. So we could not see any structural damage to the shell and the bottom slab after this tilt also. So the structure got commissioned, the tank got commissioned and is being used satisfactorily, I hope. This has happened more than 15 years ago. And what we have is learned from this case study is that design environment shall match with the actual site conditions. The stability of structures near steep slope is always at risk. And especially for the case of tank foundation, we need to have a detailed analysis of the hydrotest data to confirm the structural stability, see that the differential settlement along the periphery of the tank is not large enough to cause any structural instability. But to have these things, we need to have a close monitoring of all the structures, and we do not have a good practice of monitoring the structures in India, but that is the most required thing in any of the critical structures. When we construct, we are assuming so many parameters, but we need to have a close monitoring of the structure. How does it perform when it is being loaded? You can also see that the stage loading of storage tanks ensures stability. In this particular case, we realize that the tank is settling more when the load reached 50%. And had we continued the load without measuring the settlements, it would have failed when the load reached close to the maximum load. So the stage loading and continuous monitoring helped us to detect there was a problem with the foundations. So that is the most important part, that we should monitor any structure which is critical, or especially when the tank is holding a harmful product or hazardous product. I will come to one of my favorite project, the restoration of a cooling water channel, which is not very geotechnical in nature. Mostly it is a mechanical solution, but with a little bit geotechnical component. I came to this problem only because of geotechnical engineer, and everybody thought it is a geotechnical issue, but it was not. There was maybe the biggest, largest thermal power plant in India, maybe in NTPC Kaniha in Thalcher in Odisha state. It has roughly 1.5 kilometer cooling water system. And this cooling water system was built in late 70s or early 80s. And it was functioning well until 2016. So, and there was a damaged portion, about 55 meters the length of the cooling water channel bank damaged during November 2016 because they constructed some the cable drag system on the banks. And it started, the actual failure started in January 2016 and it magnified when it was November 2016. And you can see the damages of the bank. There was a well-defined cooling water system. You can see a lot of damage on the banks. And you can see the flow of water, which has very high velocity of 3 meters per second. A lot of damage, and these are the cable tray which is fallen into the channel, and a lot of erosion on the bank. So practically this whole area became unusable, and there was a danger of the existing structures nearby, and they have to abandon the functioning of all these structures nearby. This is the actual cross section of the channel, which was built in early 80s. Because of the rock profile, weathered rock profile on the sides, they used only a skin wall to stop the water loss through the sides. And the depth of the water was 5 meters with a freeboard of about 350 millimeters. So the maximum water level was 5.3 meter, and it may go up to 4.8 meter or so without much fluctuation. So the condition of the cooling water is it is always full or close to full, and it was never stopped after the inception of the power plant, because the plant cannot work out with the functioning of the cooling water channel. This is the damaged portion which was washed away because of some failure from the top. It started from the top because of additional loading from the cable tray. And it was to be restored because the plant has to continue. And roughly 52 meter length portion was to be restored. Fortunately, as a consolation, only the banks were damaged, but it was not damaged. And some divers tried to go on inside and see, but we assumed that the bed was not damaged, which was later confirmed by lowering long boom cranes and checked the bottom of the channel. The restraints are that the channel runs full always, and there is no shutdown to stop the cooling water channel. The velocity of flow is 2 meter, 3 meter per second, because of which no diver can safely work in the flow. And the NTPC put a work schedule of 2 to 3 months to complete the restoration. So these are the last 3 were the constraints of making any restoration work. And the thought process of restoring it started in 2016, and it was never done until 2000 November, until 2017. So this was a scheme proposed by the contractor when they were approached by NTPC. They proposed both the micropiles inside the drain, and precast panels were to be lowered through the micropile, and we need some divers to execute this work. And all this panel will be connected to the micropile, and the space between the bank and the precast members will be concreted to make it a stable structure. So this was the scheme proposed by the contractor, and unfortunately this could not be executed because of the constraints, site constraints. Nobody could go inside the flowing water, and the work, the thought process continued till 2017. So I was able to give a system in 2017 when they approached me, in which there was no job done from the waterfront. So this is the existing bed which is stable, and the sites which is damaged you can see from the picture. And what proposed was we'll have a preparation, the ground prepared for the restoration work. We'll install micropiles on the banks instead of installing it inside the tank. Initially, the micropiles were supposed to be installed here. Now, in the new scheme, the micropiles will be installed from the bank only, enough distance from the existing scheme line, the periphery of the channel. There was enough working space to install these piles. Then we'll connect these rows of piles with the primary beam, and we propose another one secondary beam close to the channel section. So almost mid-width of the distance between the micropile and the channel space. And these two primary beam and secondary beams are connected with cross beams. Then a bracket system using a sheet pile in the waterfront and H section and ISMC section as a bracket, which will take the necessary moment actions when we fill the concrete. So this was the scheme we proposed, and after placing this bracket system, we will fill the bottom with the plastic concrete, which eventually will stop the flow into the annular portion. Then we will complete the concreting in the left out place between the ground and the bracket system. And the final work will be the final platform construction and the handrail constructions. You can see the sheet piles which are proposed for this bracket system. This is more detailed section of the scheme, and this is a plan of the scheme. What we see, these two brackets, which has some ISMB sections and ISMC sections, and one section of the sheet pile. Once we put two brackets, we will place the remaining two sheet piles. You have sheet piles to close the gap. So as we get a continuous wall of sheet pile. This was the scheme proposed, and it was executed. So if you go at the sequence of the work, first we'll have two brackets placed, and we fill the gap between these two brackets by introducing sheet piles through the grooves of the sheet pile, and we continue the process until we finish the full wall length. We also made a safe platform for launching the sheet pile and the sheet pile brackets, so that nobody has to enter the water during the execution of the project. So this is the three-dimensional representation of the scheme, what we proposed for launching the sections. The first point of the activity for the restoration was to clear the channels with removing all the debris. You can see a lot of debris in the channel, which are all removed by a long boom crane. And we had the construction of the micropile filled with grout, polymer grout mix using Trummy. Then the placement of the primary and secondary beams. Then placing the platform, safety platform over the primary and secondary beam. Then launching the first bracket system through the platform. You can see the counterweight to make the platform safe. Almost half the length of the platform was overhanging into the channel. These are the pictures of the construction activity. You can see the flow of the water. You can notice a rubber shoe for the sheet pile. This rubber shoe is helping the wall system from preventing entry of the water into the enclosed section. These are another photographs of the construction sequence. We have placed an end stopper so that the water is not entering to the enclosed area, which has to be concreted later. So we use this tapered end stopper, which is made of steel. This was lowered through one of the connected to one of these U-hat sheet pile, which is lowered through the existing sheet pile glue. I will run one video of, you can see the speed of the water in the channel, whereas in the enclosed portion there is no movement of water. We could close the movement of water inside the channel. There is another video where you can see the flow of water outside the wall and practically no flow in the enclosed portion. So this was achieved by putting this end stopper. This end stopper, and no water flow was into the enclosed area. Then the plastic conduiting was done through the trummy. Then the first pour of the conduit using the trummy. And the second pour of the conduit. We had nominal steel provided in the concrete so that it has a monolithic action with the existing sheet pipe. These are the conduiting stages, different stages of conduiting. And the wall construction is in progress. Almost 60–70% of the wall was constructed and almost full. And the capping of the wall was taken up later. You can see that the mixer was able to come to very close to the wall. Is constructed. What we have to notice here is the sheet pile become almost redundant once the conduit is set, but it will protect the conduit from further erosion later. And this is the full length constructed of roughly 52 meters. And the platform, they've got much better platform for placing other structures or further work in this construction. So what we have from this case study is that rectification works are often complicated and expensive, but we can see simple solutions if we search for it. And the unfortunate part is that geotechnical engineer tries to look at all the problems as geotechnical issues. We do not like to think laterally, but we have to do that in certain cases. We also find that the simple solutions are always overlooked when we demonize the problem. And there is always a suspicious view when we provide such simple solutions, which I faced for this case also. I'll come to my last case study. I think I'll take another 5 minutes. I just wanted to tell this about the laterite blocks, which is supposed to be a very good construction material in South India, in Kerala, Karnataka, and some parts of Tamil Nadu, and in Odisha, and also in Andhra Pradesh. So we used the gabion wall for retention of 4 to 5 meter soil fill in a water treatment plant in Kerala. We proposed to use the granite as the infill for the gabion wall. While during the construction, there was a restriction on use of the granite stones because of the mining restrictions, and the contractor proposed to use locally available lateritic stone, and that was considered by the consultants. But the proposal was to use the laterite stones, not the cut block laterites. But finally, the laterite stones were not available, and it was agreed to use laterite blocks, machine-cut laterite blocks instead of the stones. These are the pictures of the these gabion wall construction retaining about 4 to 5 meter earth, which was constructed eventually. Some of the pictures you can see. This length was roughly 170 meters. You can see a lot of damage in the gabion wall constructed using these laterite blocks. The blocks were opened up. Some blocks were crushed out of the gabion net. There are more damages on the laterite blocks. When we analyzed, we found that they used fresh cut laterite blocks for the construction of these gabions. Laterite is very soft when it's freshly cut, and it requires a maturation process, a wetting and drying process, which usually we do in most of the places where they use the laterite blocks. When we allow it maturate for 1 or 2 seasons, it becomes very hard. The soft particles become hard, and the block is resisting all the weathering actions. And there is also an issue of straight joints, which we cannot avoid when we use blocks, straight cut blocks. There is a continuous straight joints. 3 joints are there in the field within a gabion box, which can move away when the load is coming or when the soft material is ready. So this was the reason for the failure of this gabion wall, some of the portion of the gabion wall, which was later rectified using thin conduit walls with V-ports. So when we use locally available building materials, we can economize the construction, but we need to select the proper material depending upon the mechanism of the system, and strength and durability conditions shall satisfy. In this particular case, we could not satisfy the third criteria, the strength and durability condition of the block, and also the second issue of such material needs selected depending on the mechanism system. The mechanism of gabion wall is that there should be proper interlocking of the infill material, which was not available in the case of laterite blocks. So as the concluding remarks, geology engineering practice is complex, and when we have a lot of case studies, well-documented case studies, it can bring the theories close to the practice and vice versa. And we need more and more well-documented case studies that will improve the quality of geological engineering practice. These are some of my concluding remarks. And today morning I received this cartoon from my daughter. In the lockdown period, we think about eat and sleep. And I thank the organizers of this webinar to tell us there is more to life than eating and sleeping. Thank you for listening.
Thank you so much, sir, for that presentation. In fact, case studies play a very vital role.
Yeah, thank you very much.
Yeah, in fact, to understand the concepts in a with much clarity, because that is one practical perspective that can be brought into. Because case studies always have the problems which is being outlined in a very clear manner, the suggested solutions and the solutions which has worked as well. So I think the construction professionals would have got from a practical perspective the entire history of what has happened and what are the solutions. There are some questions. I think we will take it up after Dr. Prasanna speaks. Let me also welcome Dr. H.S. Prasanna from National Institute of Engineering, Mysore. In fact, NI Mysore and SJC Mysore has also been, they have supported this conference apart from Association of Consulting Civil Engineers and Geotechnical Society. So over to Prasanna sir for your viewpoints.
Yes, sir. Very good afternoon to one and all of this webinar. I sincerely congratulate Mr. ANIRUDHAN IV for giving us deep insight. It gives me an immense pleasure in instance and my views later. It dates back to 2014, during which some of my esteemed colleagues in geotechnical engineering domain, to name a few, my mentor, Dr. K. Prakash, Dr. S.K. Prasad, Dr. K. Visharam, office bearers of the ACCI Mysore Center sat together and finalized the idea of conducting one-day workshop annually in geotechnical engineering domain to disseminate the knowledge of geotechnical engineering at first instance to largely due to the faculty members, working professionals, field engineers, architects, structural engineers, students of UG, PG, PhD scholars, and successfully named it as ROGI. Now it has become a prestigious national event webinar with the help of IGS India, IGS Bengaluru chapter, Ramco Cements, ICC, ACCI Mysore Center, NIE and JC Mysore for co-sponsoring the event. Let me thank personally all the sponsors of this great event. Let me unquote a famous quote by Alexander Pope. Knowledge is a dangerous thing. Drink not the Pierian spring. Its shallow thoughts intoxicates the brain. Drink it deep, it sobers us again. All of you know the Pierian spring is a spring of knowledge. Dear friends, a thorough theoretical knowledge of geotechnical engineering is very much required to be imbibed to convert into practical applications at large, catering to the needs of the society at large. The successful practical applications of geotechnical engineering may include from providing a meaningful solutions to foundations engineering problems like shallow foundations, to residential buildings, commercial establishments, to the extent of deep foundations like pile foundations for tall structures, chimneys, thermal power plants, etc. In addition to major hydraulic structures like dams, reservoirs, embankments for railways, roadways, and airways. Due to the lack of goods available for constructions, it is forcing the construction industry to go for marginal landfills by importing or adopting ground improvement techniques like static compaction, dynamic compaction, vibroflotation, sand piling, micropiling, and jet grouting, etc. This is absolutely necessary to minimize or avoid the differential or uniform settlements and shear failure of foundations, which in turn give way to the safety of the structure. Classical settlement of structures like Leaning Tower of Pisa, example of differential settlement, and to the example sinking city of the world, Mexico, uniform at large. Dear friends, the role of pre-consolidation stress at the foundation level also plays a very vital role, whether to understand the given deposit is normally consolidated, under-consolidated, or over-consolidated. Another illustrious example of ground is the Singapore International Airport. As we know, the engineering behavior of coarse-grained soils is a physical phenomenon, whereas for fine-grained soils, it's a physico-chemical phenomenon. Here, both physics and chemistry role comes into picture. And it is due to the presence of least active clay mineral like kyanite to the extent of most active clay mineral like montmorillonite. The sheer knowledge of mechanisms controlling the settlement and shear behavior of structures subjected to various gravity loadings to the extent of instant loads like wind load and earthquake is very much necessary, while advocating the practical solutions by engineering fraternity to have a meaningful and economic, which the society expects from us to a very great extent. Here, the role of technological applications from reinforced earth to rubber dams is also worth mentioning here. As you know, due to the advent of technological advances to the extent of heterogeneous behavior of soil stratification in the presence of groundwater make the problem more complex and confused one. An example of matrix, probably you might have heard: true positive, true negative, false positive, and false negative. The problems and the true positive with a subset of false negative, or a true negative subset of false negative in a cyclic order. In these situations, the role of geotechnical engineer manifests the safety of substructure, superstructure as an integral part. The threshold of flexible structures right from substructure to superstructure demands a nearly perfect engineered solution to achieve economy in 4 M's. That is men, material, machinery, and money, as rightly said by ANIRUDHAN, and even to the extent of Mr. Mohan Prasad and even Professor Madhav. In such a situation, the practical knowledge of situational solutions can be had from illustrious case studies, which was very well fabricated and delivered by ANIRUDHAN IV, CEO Geotechnical Solutions of Chennai today, made all of us rich in terms of knowledge and practical approach to engineering solutions. In order to achieve such a stage of excellence, some common misconceptions about geotechnical pass through a codal guidelines as effectively presented by NTP Mohan Prasad, CEO of Geomatrix, in yesterday's webinar. As you know very well that experience is a very good school, but my dear friends, but its fees is very costly. In the recent past, most solutions to geotechnical problems is on the rise, which necessitates the readiness for accepting such solutions within a meaningful time horizon. Here, the role of geotechnical engineer shall exercise his common sense while arrive at an economical and safe solution to foundation problems he envisaged, because you know civil engineering is a codified common sense. This approach was stated and delivered by Professor M.R. Madhav during his inaugural webinar on 14th of this month. It's high time that the at practical site situations, structural engineers and architects, instead of positioning themselves at 3 corners of a triangle, should have higher magnitude of cohesiveness, lesser degree of internal friction, and come close together to achieve a common goal of understanding within a triangle itself, thereby increasing one's individual strength and also increasing the shear strength of the subsoil, so that their common goals shall not settle beyond the exceeding limits or having shear failure. For example, I would like the role of Pareto analysis and the circle in construction organizations. That's very important, which was first coined by Japanese tape manufacturing company as early as 1967, which plays a pivotal role in bringing down the cost of foundation to a very great extent. The civil engineers at large shall exercise an integral approach than differential approach to an engineering problem at large. You know it very well, a journey of 1,000 miles begins with a single step that we have started. You know it very well, the success has been for that we have to envisage. I thank all the organizers for giving me an opportunity to share my views as a panelist today, and in the capacity of chairman of this webinar series RAGI 2020. I thank one and all. Have a nice day.
Thank you, Professor Prasanna. Being the chairperson of RAGI 2020 and being in a number of geotechnical projects for a number of years, you are the prime mover for this event. Thank you for your views. Now, Anirudhan sir, can we take some questions from the audience?
Yeah, sure. So you will
Okay,
take
now-
the questions.
Yeah, I will just, the first question is, why concrete retaining wall is not used instead of reinforced earth in wet slope tank study?
The height of the wall was something like 12 meters, and because of which the return wall was costly. So we thought the reinforced earth wall was much cheap, economical, and easy to construct. And already the area was excavated fully, so there is a necessity of filling. So during the filling itself, we can complete the construction of the retaining wall. So we have a single process in the construction retention wall that we fill as and we reinforce the soil. In the case of retention wall, we have to construct the wall, have the foundation much deeper than to take out the tilting or the lateral force, overturning the wall, etc. And the reinforced earth wall was found to be much economical, especially when the height was 12 meters.
So, another question is, instead of sheet pile wall solution in NTPC, is it good if we go for using geosynthetic reinforced wall as in landfills?
Here the main issue was closing to the water, going to the water. We could not go into the water and do any work from the waterfront. So to make a reinforced earth wall, we have to excavate further and create more width. And we were never allowed to stop the water. During the wall construction, probably the whole history of NTPC Kaniha, this channel was always full. So there was no drying period to make any other option.
Now, regarding the micro pile, there is a question. What was the diameter, length, and spacing of the micro pile as installed? What was the load carrying capacity of the micro pile? Was it designed to take care of any lateral movement of the ground?
Is it referring to the must be referring to the channel restoration?
Correct.
Yeah, these piles were, we made a bore hole of 300 diameter and lowered 250 ISH sections. And the space in the borehole, between the borehole and the section, was filled with polymer concrete. And these piles are taking only lateral load, not any vertical load. Mostly the load from the sheet pile, especially when the concreting is done. The wet concrete needs a lot of lateral thrust on the sheet pile wall. That load is to be taken by the micro pile. Once the concrete is set, there is no lateral force on the pile as well as on the sheet pile. So it's like a solid concrete. The forces are almost nil once the concrete is set. And one more thing, I'll talk about the concrete, because many people have questioned the use of normal Portland cement concrete, because of mass concrete and a lot of heat of hydration. And many are suggesting we go for slag cement or pozzolanic cement. Unfortunately, it was not readily available during the execution time. So we would prefer, for any mass concreting, we go to slag cement or pozzolanic cement, where the heat of hydration is much less.
Another question is, was the global stability check for the ground supporting the tank structure very close to the slope edge done? What is the factor of safety obtained in that case?
The design was actually done after the development of the site. The site was to be developed with the reinforced earth wall and backfilling the dike area. And then only the tank was supposed to be hydro-tested. But unfortunately, the tank was hydro-tested before making these arrangements. That was a mistake or the disconnect between the design and the construction. So there was no necessity to design the structure for this steep slope because the site was to be developed with backfill and should have been done earlier prior to the hydrotesting of the tank.
Another question on piling itself, how the working service pile which is part of the structure be allowed to be loaded to its ultimate capacity corresponding to around 10% of pile deflection which may lead to the failure of foundation soil.
Yeah, whatever I have shown is all test piles, initial test piles which are built to the ultimate capacity, or it has not reached the ultimate capacity as designed. So all these results were for the initial load test piles. So we have roughly more than 200 such load test results on test piles, which is compiled in some of my papers. And there are several routine load test results. So all these, wherever the pile failure is shown, is mostly on initial test piles. Of course, there are the cases the pile failure occurred in actually a routine pile load test also, which is not presented here.
So today's last question, as per Indian Standard Code, how many minimum settlement are considered? Any specification for minimum settlement?
The code specifies 18 millimeter under 1.5 times the pile diameter. That at the 1.5 times the safe capacity of the pile. But it all depends on the, say, as an individual pile, it can settle up to 6 to 7 mm under design load. But it all depends on the contribution from the friction and the end bearing. It varies between pile conditions. If we have piles resting in rock, we cannot allow settlement more than 2 to 3 millimeters because it amounts to having bad conduit at the bottom, or the tip is not properly resting in the rock. But whereas in friction pile, the allowable settlement can be less than 3 to 4 millimeters under working load. And the combination of end bearing and skin friction, it can go up to 6 to 8 or even 10 millimeters under the working load. So it all depends on the nature of the pile or how the pile derives its capacity.
Thank you so much, sir, for clarifying the queries of the construction professionals who had logged in. And to borrow a phrase from Prasanna sir, who is the chairman of RAGI, in fact, he had just mentioned that all the stakeholders must increase the cohesiveness and decrease the friction. That is a very good point that he has made, and I think all these lectures that has been made over the last, right from beginning, May 14th, by Professor Madhav, then Engineer Mohan Prasad and Engineer ANIRUDHAN, and tomorrow we are going to have the final presentation as part of the workshop by Professor Dadagowda, and he would be talking about materials, environment, and the pile draft foundation tomorrow. At the same time, 11 a.m., all of us can be logged in for that presentation, which I am sure that would complete the entire this thing. So we had various aspects, in fact, very nice. And now the thing is that it's our responsibility to go into the depth of what has been spoken about and to understand more clearly. So with those few words, I thank the speaker.
Can I say one comment?
Yeah, please, sir, please.
With regard to soil, it's always the friction that is important, not the. So almost all the problems on friction only.
Internal friction.
Even for clay. So.
Right.
So on the lighter
there is no end bearing load. I think it is standing on the friction itself, which is giving it support.
Whatever in long term, because all the structures are long term structures, and finally it will be governed by the friction, not from the provision. Yes.
So friction also plays a vital role in giving. That was a good one. Yeah.
Sir, I would like to add, say in friction also, there is rolling friction, interlocking friction. So as far as interlocking friction is concerned, rolling friction instead of interlocking.
Yes. Yeah,
thank you.
Yes.
So thank you, sir, ANIRUDHAN sir, for that wonderful presentation, and thanks, Prasanna sir, for driving this whole seminar. And we are thankful to all the organizers. And with those few words, on behalf of Ramco Cement, on behalf of RAGI, On behalf of all the collaborating associations, I thank you for having taken your time off and joining us for today's webinar. Thank you so much.
Thank you so much. If I have the full list of questions, I can answer if when time permits.
You have, is it okay?
No, not now.
Okay.
But if you can send me, if you can save the questions,
We will definitely do that, sir. We will send you the list of questions to you so that you can clarify and all that. So nice of you, and thanks for sparing your time, and all the best. Thank you so much, sir.
Yeah,
thank you.
Thank you. Thank you very much. Shall I close the meeting? Yeah.
Yes, please. Yes, you can leave it. Thank you.